Now let's switch to basic solutions and get progressively harder. The difference here being, of course, that now we're going to use OH minus to balance any charge needs. So there's the equation, oxidation numbers. What's reduced is the manganese. What's oxidized is the iron. MnO4 minus is, in my mind, a nicer oxidizing agent than the dichromate. It's prettier, it's not nearly as carcinogenic, and so forth. So you'll see this quite often as well when you study oxidations in organic chemistry. So when you're in acidic solution, it goes from NM4 minus to Mn2 plus. When you're in basic solution, it goes from MnO4 minus to MnO2. So let's focus in, 1 manganese on each side. Each manganese gains 3, so we need 3 electrons on the left-hand side. Oxidation, very common oxidation, Fe2 plus going to Fe3 plus an electron. 1 electron, 3 electrons, put them together. And we get this as the equation in which all the important atoms and the electrons are balanced. We do have charges, oxygens, hydrogens, so let's proceed to the next steps. Charge, total of -1 on the left, 0 on the right. So we need 1 something, and we're in basic solution, so it's 1 OH minus. What side do we put it on? The side that needs to become more negative, so that is, in this case, the right-hand side. Okay. Now let's look at oxygens, fairly straightforward, 10 and 12. So difference of 2 with the waters. What side should we put the waters on? The ones where it needs more oxygen, so that's the left-hand side. And now let's check with the hydrogens, and you might need to use your fingers for this. 2 times 2 is 4. 2 times 3 is 6. 4 plus 6 is 10 on the left. On the right, 3 times 3 is 9 plus 1, 10. Got to be worthy of a smiley face. 18, same thing again. Basic solution, making it a little bit more complicated here in reductions. NiO2 goes to NiOH2, going from 4 to 2. Oxidation, iron 0 going to iron 2 plus. Following it through, 2 electrons going from 4 to 2 for the nickel, and so therefore 2 electrons on the left-hand side. And we're obviously going to have 2 electrons on the right-hand side. So no need to do anything fancy, just bringing them together like this. Charge, 0 and 0 and 0. Don't need to worry about that. And that would make a lot of students say, oh, well, it must be good if there's no worry about the charge. No, let's count our oxygens. Got a total of 2 on the left, 4 on the right. So we need 2 waters to go on the left. Let's count our hydrogens, total of 4 on each side. So a smiley face. So the coefficient of water was 2. So it's one that, because it's so straightforward, actually becomes difficult. You don't have to worry about the important atoms. You don't have to worry about differing number of electrons. You don't have to worry about charge. And so that does tend to put students off because it seems to be just too easy. It is, but you have to watch out. So still in basic solution, coefficient of water. Obviously, as you look at it, you can see we got, first of all, some unfamiliar species with the seleniums, but we also got a difference in the number of sulfurs. So let's just go ahead, as usual, assign the oxidation numbers. Reduction, it's the sulfur. We got 2 on the right, so we need 2 on the left. Each sulfur goes from 4 to 2, so changes by 2 electrons. We got 2 sulfurs, so we need 4 electrons on the left-hand side. For selenium, relatively straightforward, -2 to 0. So we obviously need 2 electrons on the right-hand side. I would return 2 to 4, multiply the 2 by 2. And so this is the seleniums and the sulfurs are balanced and the electrons are balanced. Charge, total charge on the left. 2 times -2 is -4, 2 times -2, -4, -4, -4, -8. Over here, the only thing is the thiosulfate. Hope you'll recognize that as being thiosulfate. -2, so we're off by 6. We need OH minuses because we're in basic solution. Now go on the side that needs to become more negative, which is the right-hand side. So that's our 6 OHs there. Oxygens, 6 and 9. Got 3 there, plus 6 times 1, 6. 3 plus 6 is 9. So we need 3 waters. Go on the side that needs more oxygens, which will be the left-hand side. And now check with the hydrogens, 6 and, fortunately, 6. Final equation, let's do a disproportionation in basic solution. Okay, so ClO2 there going to ClO2 minus, ClO3 minus, throw in the oxidation numbers. The reduction is going from ClO2 to ClO2 minus, 4 to 3. The oxidation is going from ClO2 with a 4 oxidation number up to ClO3 minus with a 5 oxidation number. So proceeding on through, for the reduction, 4 to 3, 1 electron per chlorine. And for the oxidation, 4 to 5, 1 electron per chlorine. And so we get this, put them together, and we get ClO2 plus ClO2 goes ClO2 minus, ClO2 minus. Obviously, we got 2 ClO2s, so we'll put them together like that. You can obviously see that's an immediate difference in charge and oxygen, so let's proceed with the charge. 0 on the left, minus 2 on the right, so we need 2 OH minuses, which will therefore go on the left. Okay, so again, this is an exception to what some people say is a generalization. OH minus goes on the right. No, it goes on the side that needs it the most, which in this case is the left. Looking at the oxygens, 6 and 5, so we need a water. What side should we put the water on? The side that needs it, so therefore that is the right-hand side. And now let us balance H's, total of 2 and 2. So our final big nasty equation is balanced. Again, onto the ratio of the coefficients, 2 to 1.